Okay, so I'll be going over the FRQs from the Unit 5 progress check. So here's the first one. We have a disk and a cylinder that's sitting on top of the disk. And the disk has a moment of inertia of 1/2 mr squared. And we're dealing with a small cylinder that also has a mass m that is 1/2 r away from the center. So something I want to mention here with the small cylinder, the fact that it's a small cylinder is important because basically we can ignore the parallel axis theorem. So normally if you have an object that's rotating around some point that is not the center, you have to add an md squared term, right, which is how far away the axis of rotation is from the center of the rotating object. But given that's a small cylinder, right, so in other words, the radius of the cylinder is insignificant compared to how far away it is from the axis of rotation, we can just treat it as a point mass. So that's important to note. And we have here a function that describes the angular velocity of the system. Before I even get to the first part of the problem, I want to talk about what this function means, just to make sure we understand it. So what this is saying is that as time goes on, we have this decaying exponential term, and we're going to notice that the angular velocity is going to approach omega f. All right. So when you look at this kind of function, right, just think about, what is it? What happens when t equals 0, and what happens when t approaches infinity? Well, at t equals 0, I have e raised to negative 0, which is 1. 1 minus 1 is 0, right? So then that times omega f is 0. It starts off with 0 angular velocity, and then the angular velocity approaches omega f. And I can just do a little sketch here just so we can visualize it. So it asymptotically approaches its final angular velocity, and it kind of looks like that. Yeah, I think it's good to know what this function is saying before we even get started. So here we have to derive an expression for the maximum torque exerted on the cylinder disk system about the disk's center. And so in order to do that, what we're going to do is use Newton's second law of rotations. So we know that torque is equal to I times alpha. And all I need to do is find an expression for a moment of inertia and for angular acceleration, which I'll do now. So the moment of inertia of the system, we have the disk, which is 1/2 mr squared. So 1/2 mr squared for the disk, plus the moment of inertia of the small cylinder, which we'll treat as a point mass. So it has moment of inertia of mr squared. But don't forget, the radius is r over 2. So it's r over 2 quantity squared. R over 2 squared is r squared over 4. So I have mr squared over 4, and we got our 1/2 mr squared from our, oops, I forgot to put the squared there, from the disk, and I add these two together, use common denominators, I end up with 3 over 4 mr squared. Okay. Now for the angular acceleration, we have a function for angular velocity. To get angular acceleration, we need to take the derivative of the angular velocity with respect to time. And I'll do that now. So d over dt. When doing the derivative, I'm just going to distribute this omega f term, just so it's more clear as to what's going on. So I have omega f minus omega f times e to negative t over tau. And then let's remember the power rule when it comes to dealing with an exponential. So if I take, say, d over dx of e to the c times x, right, I get c times e to the x. So I just bring that coefficient down, or e times c times e to the cx, right? So yeah, that's pretty much it. Let's set this up. So I'm taking the derivative with respect to time. So the coefficient in front of the t is negative 1 over tau, basically. And then when I take the derivative of omega f, right, so this omega f term over here, okay, that term is going to end up being 0 because the derivative of a constant is 0. So I end up with negative omega f. So like this part doesn't matter, but the omega f times e to negative t over tau, that's what we care about. So I'm going to bring down that constant in front of the t, which is negative 1 over tau. right? And then multiply by e to the negative t over tau. Let's clean this up a bit. So negative omega f times negative 1 over tau is basically just omega f over tau times e to negative t over tau. All right, so I have an expression for angular acceleration, and I'm going to multiply it by my expression for the moment of inertia, right? So I got my angular acceleration here, my moment of inertia here, and then I'll put them together to get the torque, the net torque on the system. Now, let's just write the expression. So we have 3/4 mr squared times this omega f over tau times e to negative t over tau. Now, don't forget, this is asking about the maximum net torque. All right, so let's think about this function, right? When is this function maximized? Well, if I have this e to the negative t over tau at t equals 0, right, I have e raised to the negative 0, which is pretty much 1. So then I just have like the expression that's in front of the exponential here. And then as t approaches infinity, e to the negative infinity is equal to 0, right? So the torque is going to approach 0, right? Which kind of makes sense. If we think of torque's related to angular acceleration, and if we look at our sketch that I made earlier, right, the angular velocity is asymptotically approaching the final angular velocity, where the slope at that point, as t gets very large, the slope's practically 0. So let's write our expression here. So tau, or not tau. Well, it's actually slightly annoying, right? Because this one we're using, oh, goodness. That's why they use capital T. Oh, man. All right, because we're using tau for torque, but it's capital T for the time constant, right? Yeah, okay. All right, well, anyways, it doesn't make a difference in terms of the analysis. I kind of see why they used positive T in this case, just so you don't mix up with the torque. But I mean, all right, it's the same analysis, right? All right, we're going to use capital T instead for the final expression. So my max torque is going to be 3/4 mr squared times the omega f over t. All right, omega f over capital T. Okay. All right, 1 second. Okay, so now we're gonna move on to part 2. So we have the frictional force that acts on the cylinder at times t equals capital T. All right. Indicate whether this force has a tangential component only, a radial component only, or both a tangential and radial component, and justify your answer. So for this one, it's a little tricky because basically what's going to be happening Okay, anyways, so here, there's two things happening. So this, obviously this system has an angular acceleration, and because it has an angular acceleration, there has to be a tangential acceleration. So let's just write that down. So I'm going to draw it. I'm actually just going to draw it on the diagram and then kind of explain it at the same time. So here, so imagine this cylinder is rotating around, from our perspective, it's rotating around counterclockwise. All right. So there's an angular acceleration also going around here, right? As we established, given that there's a net torque. So that means there has to be a tangential acceleration. I'm going to draw it on here. So like, it's kind of going this way. There's a tangential acceleration. Okay. But there also has to be a radial acceleration. So the radial acceleration is going towards the center of the circle. So there's a I'm going to call it the radial acceleration. All right. Is that yeah, so there's a tangential component, there's a radial component. Now, why is there a radial acceleration? Because there has to be a centripetal acceleration, right? So my tangential acceleration, I'll even write out what the values are. So my tangential acceleration is alpha times r, and my centripetal acceleration is going to be omega squared times r. All right. So yeah, basically anything that's moving around in the circle, right? So this cylinder has some mass and it's moving around in a circle. There has to be some acceleration that is pointing towards the center of the circle. That's a centripetal acceleration. And because the rotation rate of the disk is increasing, right? There's an angular acceleration. That also means that there's a tangential acceleration. Now there has to be a force that provides those accelerations. And it just so happens that that's the frictional force, right? That's a force that is parallel to the plane that is actually keeping the cylinder on top of the disk, right? If the disk was rotating really, really, really fast to overcome the frictional force, the cylinder would fly off. So that's the idea. That's the argument. You would just say that it has a tangential acceleration because it has an angular acceleration, and this relationship holds, right? Tangential acceleration equals angular acceleration times radius, and then it has to have a centripetal acceleration because anything moving in a circle with some angular velocity has to have some centripetal acceleration that keeps it going in that circle. Then we have to derive an expression for magnitude of the linear acceleration of the disk at an instant when the angular speed of the disk is omega f over 3. All right, so this is going to require a bit of calculation, but it's not too bad. So if omega is equal to omega f over 3, what we need to do is we have to solve for the time constant. So I'm just going to write out this expression here. So when the angular speed of the disk is omega f over 3. So I'm going to rewrite this expression here, the expression for the angular velocity of the disk. So omega is equal to omega f times 1 minus e to the negative t over capital T. All right. And if at a point where the angular velocity is omega f over 3, that equals omega f minus omega f times e to negative t over capital T. All right. And then what I'm going to do is I'm going to move this omega f over to the other side. All right. So I'll subtract both sides. Actually, it makes more sense to write it out like this. All right. So I'm going to write, I'm going to do multiple algebra steps at the same time for the sake of time. I don't want to spend too much time on this. So I have omega f times e to negative t over capital T is equal to omega f minus omega f over 3. All right, and that basically becomes 2 times omega f over 3. Whoops, I want to use the smaller pen. So then that means that e to negative t over tau is equal to 2 over 3. All right. So now we have an expression for e to negative t over tau. We can then plug that in to the angular acceleration to figure out what the angular acceleration is. And then once we know the angular acceleration, we can figure out the tangential acceleration. And then we're going to do something similar for figuring out the centripetal acceleration. So first, let's find the angular acceleration. All right, I'm kind of running out of space up there, so I'm going to put it down here. We have our expression from before, right? Where was our expression? Let's see. Yeah. So here we go. We have omega f over t, capital T times e to negative t over tau, right? So we have here yeah, so omega f over capital T times e to the negative t over capital T. And then this whole term we just established has to be 2 over 3, right? So then I have 2 over 3 times omega f over t. That's going to be my angular acceleration. And then the relationship between angular acceleration and tangential acceleration is just alpha times r, right? So my tangential acceleration is 2 over 3 times omega f over t times r, all right? Now I have to also consider the centripetal acceleration. So I know the centripetal acceleration is omega squared times r, right? And then our omega is going to be omega f over 3, right? So I have here omega f over 3 quantity squared times r, and that's going to be omega f squared times r over 9, right? Because 3 squared is going to be 9. And, ooh, whoa, I almost made a huge mistake. Oh, my goodness. Okay, so we're considering the angular acceleration of the cylinder, the linear acceleration of the cylinder. So the cylinder, okay, it's at a radius r over 2. All right, so let's work back here. All right, so I have here an expression for the tangential acceleration. So it's not at a distance r away from the center. It's at a distance r over 2, right? So I have omega f over t times r over 2, all right? So I'm going to rewrite this as 1/3 omega f over t times r, all right? And then the same deal over here. It's not r, it's r over 2, right? Because that's where the cylinder is. It's at a distance r over 2. So r over 2. And then here, I'm just going to write r and then change the 9 to an 18. Okay, there we go. Now we can figure out the linear acceleration. So it's a combination of these two accelerations, but these accelerations are at a right angle. So what I actually have to do is use the Pythagorean theorem, right? So I'm going to use the Pythagorean theorem. I have a vertical and a horizontal component, and I got to find the total linear acceleration. So I have to do sum of the squares. So here I have I'm just going to put a total, okay, is equal to the square root of my tangential acceleration squared plus my centripetal acceleration squared. All right, and now this is where it gets slightly annoying with the algebra, but I have here 1/3. All right, I'm just going to write it all out. So I have omega f times r, omega f times r over 3t quantity squared plus omega f squared times r over 18 quantity squared. Okay, now if I evaluate all of this, I'm going to end up with omega f squared over times r squared over 9t squared plus omega f squared, or now it's omega f to the 4th times r to the 4th. This gets very tedious. I will show the algebra steps, but just be careful with them. All right, so then this is my total acceleration. All right, so my total acceleration is a square root. I'm going to need a lot of space here. So I have omega f squared times r squared over 9t squared, okay, plus omega f to the 4th times r squared all over 18. Nope, it's 18 squared. It might have been easier to factor out. earlier. Yeah. All right. Well, anyways, let's just do it like this. So I have here 18 squared, 324. All right, and now let's see if I can factor out a 9. I should be able to on the denominator. Yep, so that's over 36. So now what I'm going to do is I'm going to factor out some terms because there's like terms in both of these. Okay, so that's going to equal square root of, so I can factor out an omega f squared, I can factor out an r squared, I can factor out a 9, and I can't, well, I mean, that's pretty much it, right? So I have omega f squared r squared over 9 times 1 over t squared plus omega f squared over 324 divided by 9, which comes out to 36. And then these can all be removed from the square root, right? So I basically have the square root of all this times the square root of all this. And that is going to give me omega f times r over 3 times the square root of 1 over t squared minus, or I'm sorry, plus omega f squared over 36. And that's my final answer. A little bit annoying when it comes to algebra, but that's how it is sometimes. And yeah, that's it. So now let's move on to the next one, if I can. How do I get rid of this? Okay, whatever. All right, so here, yes, this is number 2. All right, so we have a pulley and a block, and this block is going to be accelerating down the plane, and this pulley has a moment of inertia of 1/3 mr. Oh, I got to do the markup. Yeah, so this pulley has a moment of inertia of 1/3 mr squared. Because this pulley has a non-uniform mass distribution, and we have some angle phi from the horizontal, and we need to figure out how to draw and label the forces. Okay, so this is going to be tricky, so you have to be careful because this is different from your normal everyday free body diagrams, because the position of where the force is being applied is important. Okay, so starting, so clearly indicate at which point on the pulley each force is exerted. All right, so don't mess this up. So here we have to think about all the forces. Well, first of all, a good force to start with is the force of gravity, right? So this pulley has some weight, so that's the force of gravity. Some other forces, well, there's this string that's pulling on the pulley, all right, and it's pulling on it from the bottom here. All right, so I'm going to put a force here, and that's going to be, all right, I'm trying to draw it on the dotted lines, but I also want to make it clear. All right, now, you know, we're going to be thorough here. We're going to make sure we make a nice, clear, clean, free body diagram. So here at the very bottom, okay, there's going to be a force of tension, okay, and this pulley, in terms of figuring out the direction of the other force, well, we know this pulley is not accelerating linearly, right? It has a rotational acceleration about its center, but the center of mass of the pulley does not translate, right? It stays in place. So I'm going to need another force that's going to balance out these two forces. So it needs to have a component going up and a component going up and to the left. But we can't draw components. We have to kind of like just draw the force. They're not too big of a stickler on this. If you're using a pencil, you can kind of like trace it out, right? If you want to get it like a good feel for it, right? So I have this vector here, and I have this vector here. So it's going to be like ending here, right? So that's something that you might want to do if you really want to draw it perfect. But as long as you have a force that's going up and to the left, and it's larger than these individual forces, then you got it. And I'll call that force, that's the force of Well, the pulley is rotating around the center, right, around the axle. So that axle has to be pulling on the pulley, right, up and to the left. All right. So this is a more challenging free body diagram. So the point of application is important. So the fact that the pulley is getting pulled with the rope from the bottom of the pulley, that's important. Whereas the other two forces, they act on the center. All right, so now we have to figure out, well, I think I skipped one. So here we have to derive an expression for the linear acceleration A as it's sliding down the incline. Express your answer in terms of m, r, phi, and physical constant. So this box is going to be accelerating down, and this pulley is going to be rotating at the same time. So what I'm going to need to do is I need to relate the accelerations together. So the angular acceleration of the pulley, I have to relate it to the linear acceleration of the block. And the way I'm going to do that is I'm going to use Newton's second law for rotations and for translations. So for rotations, I know that the net torque is equal to the moment of inertia of the pulley times the angular acceleration. And I know that that net torque is going to be provided by the tension force. Now, the reason I know that only tension is providing the net torque is because, well, let's think about it. In order for there to be a torque, you have to have some force times moment arm, right? So it has to be, that force has to be applied away from the axis of rotation. Well, the axis of rotation is right down the middle. So the gravity of the weight of the pulley and the force of the axle holding the pulley in place, they're not going to exert a torque. Only the tension force from the string exerts a torque on the pulley. So I'm going to set this equal to the force of tension times the radius of the pulley. And then I'm going to write an expression for moment of inertia. So this is a funky pulley that has a moment of inertia of 1/3 mr squared. So we have 1/3 mr squared times alpha. All right, that equals the force of tension times r. All right. Something else I can do is I can relate the angular acceleration of the pulley with the tangential acceleration at the bottom. All right, and that's going to be the relationship because A equals alpha times R, so alpha equals A over R. So then I'll be doing that. I have 1/3 mr squared times A over R, and that equals F of t times R. So one of the R's are going to cancel from here, here, and here, and then these R's cancel. And then basically what I have here is that the tension force has to equal 1/3 ma. All right, and I'm going to use this fact in order to figure out what the acceleration is, right? So I have an expression for the acceleration in terms of the force of tension. And now let's look at the linear acceleration here, right? So all I have here is, so I have the component of gravity that's parallel to the plane, and it's at some angle phi, right? So this component that's actually accelerating the box down, that component is mg mg sine theta. It's mg sine theta, and then I have tension pulling up on the block this way, all right? And then this block's going to be accelerating, so this component of gravity has to be greater than the force of tension. So I'm going to write, for Newton's second law in translations, I have ma is equal to mg times sine of phi minus the force of tension. And then I'm going to substitute for my force of tension the expression that I got over here. So I know it's equal to 1/3 times ma, right? So it's minus 1/3 ma. And then what I'll do is I'll add this term to both sides. So I have 4/3 ma is equal to mg sine theta. No, why do I? Yeah. Sine phi. Okay. So mg sine phi. And then basically one of the m's cancels out. And then I can get my final expression for A. So A is equal to 3/4 times g sine phi. All right, and that's our answer. Let's see. That was part B. Now part C, on the axes below, sketch the following. So the Pauli's angular displacement, delta theta, the angular velocity, and the angular acceleration. All right, well, let's do the angular acceleration first. So we know that it's 3/4 g sine phi. So I got 1, 2, 3, 4. Well, hold on a second. Let's start 0 here. So like say it's 1, 2, 3, 4. It's like here. All right, there's no like clean divisions. But the angular acceleration, well, if the acceleration is 3/4 g sine theta, and angular acceleration is just a over r, so then it'd be 3/4 g sine theta over r, right? So here I have, I'm sorry, not theta, phi. So here I have g sine phi over r, and then this point right here, that's 3/4 times g sine phi over r. Okay, so that's the angular acceleration. It's just going to be a horizontal line. It's just a constant angular acceleration. And if I have a constant angular acceleration and I start from rest, then I have a angular velocity with a constant positive slope. And then for my angular displacement, right, basically you do the integral again and you end up with a parabola. So I should end up with a parabola for that one. For D, indicate. All right, so now it's moved to another incline with the same dimensions. However, there's now friction between the block and the new incline. And we need to compare the original tension in the string with the new tension in the string. And this time there is friction. All right, so this one's fairly easy to explain, right? So let's think about what's going on. So now there's going to be some friction. So basically I'm adding another force over here. So now I have a force of friction that's going to be just going to reduce the acceleration of the block. So if I reduce the acceleration of the block, that reduces the angular acceleration of the pulley. And oh, we have to see how the tension. Well, the angular acceleration of the pulley depends on the tension, right? So I'm not going to write it out because it says explain it to justify the answer. So I'm going to justify it with the equations we were written down. So angular acceleration of the pulley depends on the tension force. And we know that if I add a friction force here, that the acceleration of the block has to decrease, right? Because my previous expression, where did I put the acceleration of the, so the acceleration of the block is 3/4 g sine phi. But then if I add a friction force on my free body diagram, I have to change my net force equation, right? So now I have to minus this force of friction here, right? That's going to be mu times mg cosine phi. That doesn't really matter. All that matters is that I'm going to have this friction force here, so minus the force of friction divided by m. All right, so that's like a g cosine phi term, or mu times g cosine phi term. But that's basically the argument. So that's the justification. So the acceleration of the block has to decrease, and if the acceleration of the block decreases, right, obviously that's directly related to the tension in the string. So that means the tension in the string will have to decrease, right? So that's the answer there. How does the original tension compare to the new tension? The original tension was stronger than the new tension. All right, so we're all done with that. Let's move on to 3. So this one here, we have a friction pad and a wheel. And what we need to do is design an experiment to measure the coefficient of kinetic friction between the wheel's rim and the friction pad, and we have to describe a procedure. All right, so for these kind of FRQs, I'm just going to go through the scoring guideline just because there's a lot going on, and for me to show the data and come up with data, that takes a long time. But let me give a general gist before we even look at the some examples. Basically, what you need to do for every single experiment, you have to think, what am I measuring? What am I changing as the experimentalist? And then trying to linearize your independent and dependent variables. Like, so how do I have to manipulate the equations that are relevant to the experiment in order to try to draw a straight line. So here, if we're trying to solve for mu sub k, well, we're going to need to measure the amount of friction acting on the wheel. And if we can't do that directly, right, what we're going to need to do is we're going to have to relate it to the motion of the wheel. So let's say for this experiment, you spin the wheel, you measure how fast the wheel is spinning, you apply the brakes on the wheel, and the wheel is going to slow down to a stop. I did write down some stuff for this one because I do kind of go through them. So yeah, you're going to want to either measure the angular displacement of the wheel as the wheel comes to a stop, right? So I could do that, right? I can measure the angular displacement of the wheel as the wheel comes to a stop. Let me mark this up. Yeah, as the wheel comes to... All right. So here I have alpha. So I could either do it based on the angular displacement, right? So I'd be basically thinking about this situation plus 2 alpha theta, right? And I could measure this, or I can calculate it, right? So I'd measure the angular displacement, or you can measure the amount of time it takes, right? So if I measure the amount of time it takes, then that's just a change in omega over t, right? Now, the reason we need to know the angular acceleration is because basically when this friction pad, when the brakes are applied, there's going to be a force of friction acting on the wheel, all right, that is going to exert a torque on the wheel that's going to slow the wheel down, right, assuming the wheel's rotating like this, right? So if the wheel's rotating like this, the friction's going to apply a force going down that way, which applies a torque, which slows down the wheel to a stop. And that's basically how we're going to calculate the friction in the experiment. But to get coefficient of friction, right, you have to also think about the normal force. So again, when you have these experiment-based questions, just think about what's going on, write down some equations so that you can get some guidance on what you need to measure and what you need to calculate to get whatever quantity that you're looking for. So to get coefficient of friction, I'm going to need to calculate or measure force of friction, and then calculate or measure normal force. So we can measure the normal force by attaching a force sensor to the friction pad. And then for the force of friction, what we want to do is we want to calculate it by measuring the rate of rotation of the wheel, or at least either how much the wheel spins, like how many revolutions does the wheel make, or how many radians does the wheel displace, or you can measure the amount of time it takes for the wheel to come to a stop. Yeah. So, and some other things that are important with any experimental procedure is include the measurements being made along with the corresponding equipment. So you need a force sensor. You're going to need to measure the angular velocity, right? So you can either use a camera, right? So you can put like a little piece of tape on the wheel and just kind of track its position by recording the revolutions of the wheel. You need to know how big the wheel is, so you're going to need a meter stick to measure the radius of the wheel. You're going to need to measure the mass of the wheel, right? So it says unknown mass, so you're going to measure the mass of the wheel using a scale. And then once you do all that, you can calculate the moment of inertia. Once you know the moment of inertia, you can also calculate the angular acceleration by either measuring how much the wheel rotates in the process of stopping, or by measuring the amount of time it takes for the wheel to stop. From that, you can get the net torque on the wheel. If you know the net torque on the wheel, you can calculate what the force of friction is on the wheel, and then you can measure the normal force by using your force probe. And then once you have calculated the force of friction and you've measured the normal force, then you can calculate the coefficient of friction. And then to reduce experimental uncertainty, you're going to do multiple trials. And you're going to collect the data over a range of values, right? So that's pretty much it. And I think the only other thing to mention is determine what variable you're going to change. So the scoring guideline on this is pretty broad. As long as you are just changing one variable while holding other variables constant and then measuring some other variable, right? So as long as you're specifying an independent, a dependent variable, and holding everything else constant, you're going to receive the points for that. So let's see some of the examples that those example responses they had. So for, is this one it? No, it's this one. So they measure the mass of the wheel using a balance. Okay, they measure the diameter of the wheel. They in this one they place the friction pad on top. They spin the wheel. They allow it to rotate 10 times using a stopwatch, and then place the weight in the friction pad on top, and then the combined downward force on the wheel is what actually slows it down to a stop. They measure the time, and then they repeat this procedure with the same mass applying the force, but different initial angular velocities. So for this one, they chose the angular velocities as their independent, and the dependent is the amount of time it takes to stop. All right, so then in this case, they held their normal force constant. And I think in the other experiment, this one, they changed the normal force. So they spin it with the same angular velocity, and they're changing the normal force to figure out the coefficient of friction. And then they mention repeat the steps 3 more times, total 5 trials, right? Yeah, and that's pretty much it. So now what we're going to do is look at determine how the students can create a linear graph and how that graph can be analyzed to determine mu sub k. So this one is going to be a bit tedious. I could go over all the possibilities, but in the interest of time, I think this one makes the most sense. So what you would want to do is you can measure the normal force acting on the wheel, okay? Or you can measure the time it takes for the wheel to stop. So for our independent variable, for our dependent variable, that'd be the amount of time it takes for the wheel to stop. And then for our independent variable, we're going to want to choose something that's going to give us a linear graph. All right, so here we have for data collected, procedure part A, describe how the students can create a linear graph. So basically what I need to do is, let's say we measure the time, right? And then let's look at our equation. So I have I alpha is equal to the net torque acting on the system, which is mu times normal force times R, right? So that's the net torque acting on the system. And then we can measure the initial angular velocity. So I know that angular acceleration is the change in angular velocity over time. And the change in angular velocity, where its final velocity is going to be 0. So let's just look at the magnitude of that. So I times omega over t is equal to mu times normal force times R. And we want to try to get mu from so we want mu to be the slope, right? So somehow mu it's either going to be 1 over mu or mu. But let's write out our expression. So I want t to be my dependent variable. T depends on the independent. Okay, and our independent variable is going to be normal force. So we're going to apply the brakes with varying amounts of force, right? So we're going to have a force sensor. We're going to apply with varying amounts of force. So basically, I'm going to write it a function in terms of t. So t is going to equal, let's see, this is r. So t is equal to I omega over mu times R times 1 over the normal force. Okay, so this I omega over mu times R. Actually, I think it might make more sense to do... yeah, this is slightly tedious. But yeah, you could do this, right? If I measure t, or let's say if I measure 1 over t, would that make more sense? Right, so if I have 1 over t, I would have mu times Fn times R divided by I omega. Okay, so mu R over I omega okay, times normal force. So yeah, you can either plot t versus 1 over normal force, and the slope is going to be proportional to, because all these other values are constant moment of inertia. We're going to hold the angular velocity constant, and then the radius doesn't change either. So in this case, it's asking describe and how the graph can be analyzed to determine mu sub k. So for this kind of graph, the slope would equal I omega times mu r. Okay, so say I did this one. So then the slope, I'd have some data points. I get a slope. And then I have mu omega times, so the slope would equal I omega over mu times r. So then mu would equal I omega over the slope times r. All right, so that's one way to do it. And then I could also do it the other way. I could measure inverse time and normal force. And if you think about it, this kind of makes sense, right? So there should be inversely proportional, right? Like in terms of normal force and time. If I apply the brakes with more force, it's going to take less time to stop the wheel, right? So I know that mathematically, or at least you have this relationship. What I did is I linearized the graph, right? So if say we measured time t on our vertical, right? Then that's going to be my vertical. This is my slope. And then this is my horizontal axis. That's my vertical axis and my horizontal axis. And that's what the slope represents, I omega over mu times r. And yeah, that's how you would create a straight line. And now for this one is a little tricky because of the way you have to manipulate the equations. And also this is one where the data that you have to get is actually on the y-intercept, right? So you're not going to actually be looking at the slope. What you're going to be looking at is the y-intercept for the function. So let me explain. We have this initial moment of inertia for wheel 2. So it's a new experiment, and it has some moment of inertia I2 that cannot be calculated from the wheel's mass and radius. There's no hub, so the wheel cannot be directly mounted, and then they have to experimentally determine I2. And the way they're going to do that is they're going to measure the amount of time it takes for 8 rotations. So they apply a constant torque in each of these experiments, right? So they hold the torque constant, and they're just going to measure the amount of time it takes to accelerate and rotate up to 8 full rotations, right? So as the number of spokes increase for a constant torque of 0.5, it's going to take more time for it to reach 8 rotations. Now, the math for this setup is a bit tedious, but here's the basic idea. All right, so I know that the torque on the system is equal to the moment of inertia of the system times the angular acceleration. All right, and now I'm specifying system because we're adding these bars here, right? So as I add bars, I'm increasing the moment of inertia of the system. And the way I'm going to write it is the moment of inertia of the system. Yeah, let me write this separate thing. So moment of inertia of the system is equal to, let's see here, we have the moment of inertia of the wheel plus the moment of inertia of the spokes, right? So I have the number of spokes times the moment of inertia of each set of spokes, right? So we have 2 spokes and 4 spokes and 6 spokes. So yeah, that's pretty much it. And I need to relate the system's moment of inertia with the amount of time it takes to do 8 rotations. So that's where alpha comes along. All right, so for alpha, I got to relate theta and t with respect to alpha. So the expression I'll use is theta is equal to omega naught t plus 1/2 alpha t squared. And we're going to assume that omega naught is 0. So this is a relationship between, so alpha is equal to 2 theta over t squared. Okay. And we know the torque on the system is 0.5, so that's our constant. So if I want to create a relationship where the amount of time is dependent on the number of spokes on the wheel. Okay, what I'm going to end up writing here is, let's see here. So I have alpha in terms of 2 theta over t squared. And I know that this torque on the system has to equal 0.5, right? And so that's tau naught. And I need to relate it to the moment of inertia of the system. Okay, so I have my I2 is what I'm trying to measure, plus n times I of the system, or the moment of inertia of the spokes. Okay, that's my independent variable. And all of that times alpha has to equal the torque on the system. So this is all going to equal tau naught over alpha. And then alpha is 2 theta over t squared. So this is going to be tau naught over times t squared over 2 theta. Okay. And basically what I'm going to want to do is figure out that the slope is some constant value. So I'll rewrite this as, so t squared is equal to 2 theta over tau naught times n times the number of spokes, okay, or over the moment of inertia of each spoke. Now, we don't necessarily know what the moment of inertia of each spoke is, but we can effectively figure it out by looking at the y-intercept. So this is why it gets complicated, because then we have this term here, which is I2, which is what we care about, but then we still got to worry about this 2 theta over the constant torque. But we know that theta is equal to 8 rotations, which is 16 pi radians. And if I plot, so given that I don't know the moment of inertia of the spokes, what I want to eventually plot is t squared over n. And even though we don't know what the moment of inertia of the spokes are, I know that when there are no spokes, it still takes some time for the wheel to accelerate up to speed, right? To get to 8 rotations. It should take even less time if there's no spokes on it. So there's going to be this y-intercept here, and I'm going to use the y. This is going to give me a straight line relationship by the virtue of that, like these are all, this is a linear equation, right? So I have here this slope here, right? So technically the slope is going to be times the I of the system. So I'll remove that here. So that's my slope. This is my x. This is my slope. This is my vertical axis. And then this here is my y-intercept. This is the plus b part. So then the y-intercept here is going to give me the moment of inertia of just the wheel, right? So I'll calculate what t squared is at that point of time. The number of spokes can be 0. So, when n equals 0, then my y-intercept is going to be equal to t squared, and then t squared when n equals 0, right? So that's going to equal I2 times 2 theta over the torque, okay? And then that means that the moment of inertia of the wheel is going to be equal to whatever that value is for t squared for the y-intercept, and then I'm going to I'll just write b, right, because that's what the y-intercept is, right? So I'm going to do, actually I'll just write it out. So whatever the y-intercept is times the torque, because it's a constant value, divided by 2 theta, where theta is 8 rotations, which is 16 pi radians. So that's how you do it. It's a bit much, All right, so now to answer the questions, I'll do t squared versus, oh, whoops, that's vertical axis versus horizontal axis. So here I have horizontal axis is going to be the number of spokes, vertical axis t squared. All right, on the grid below, all right, I'm not doing that. I'll show you the example. Let's see a good example. All right. All right, so it gets tedious, right? So keep in mind, there's only 4 FRQs on the actual AP exam, and you get 90 minutes for it. So these kind of questions, the ones where you have to set up some graphs and do a bunch of calculations and come up with your calculated columns, and you have your original columns, it's very time consuming. But that's part of the process, okay? So anyways, we plot this data. We get something along the lines of this. There's a y-intercept here. You're going to look at that y-intercept to figure out what the moment of inertia of just the wheel is. All right, and that's what they do here. Notice that there's many different approaches that you can take, but on the horizontal axis, you do have to have the number of spokes, okay? And yeah, this is basically what we got. All right, so that was a tough, I would say that was a tough one to set up because there's a lot going on, and the data they give you doesn't like directly lead you to the answer. You kind of have to really understand what the graph is saying, because there's so many of these problems where the slope is how we get the value that we care about. But for this particular problem, it's actually going to be the y-intercept. The slope is going to equal the 2 theta times the moment of inertia of the spokes over the torque of 0.5. And we don't even know what the moment of inertia of the spokes are, but it turns out to not matter because we see the general trend, right? So there's this general trend in the data. And from that, we know when the spokes, we're basically predicting, or we're calculating what the amount of time it would take to get to 8 rotations if I set the number of spokes to 0, right? So I see, that's kind of the idea. All right, that's almost done. It's taking a bit longer than I hoped. So I'll try to go through this one. This one doesn't take much time, so let's mark this one up. All right, so I have 2 situations, 2 pulleys. They're all identical, except this one is with a rope that has mass, and this one is just a block. And those 2 masses are the same. And then the mass of the pulleys are M1. So I have M1 here. Oh, come on. Okay, so I have M1 here, and I have M1 over here, and then the hanging mass is M2. Okay, so there are a lot of conditions for this one in order for the problem to technically work out. So I kind of get the spirit of what they're trying to do here. They're making the system more interesting by having a rope with some linear density and some mass, and the mass is hanging down. When I was reading the problem, at first I was a little annoyed because I thought that the system, the way they set it up, was a bit tricky and unphysical. But they do mention a very important fact. So here, at all times, the section of the rope that is wrapped around pulley 2 does not contribute significantly to the rotational inertia of the pulley 2 rope system. And they tell you that M2 is much less than M1. So this mass here that's pulling the pulleys, like these are some monster pulleys, right? Some giant flywheels. And these little, got this little itty bitty block and this little teeny tiny rope. And so the angular acceleration is really small. So you don't have to worry about the acceleration of the actual mass of the rope itself. That's one thing. The thing that I was originally annoyed with is that the moment of inertia around this figure 2 should be larger because there is a massive rope wrapped around the wheel. But then this is why it's so important to read the problem. We're assuming that that moment of inertia is insignificant, right? So the wheel is, so the pulley is so much more massive than the rope that you can just ignore the rope. All right. So that does make the answer more clear, right? So you'll see why. It has to do with the first question. So the question is, the pulleys are released and they begin rotating, and at some instantaneous, at some non-zero time delta t, you have to figure out what the instantaneous angular speeds are for each pulley. Is it greater for pulley 1, for pulley 2, or is it the same? Now, because the mass of the rope doesn't matter, like the rotational inertia of the rope is insignificant, we have to think about what's happening as the system is falling. So as M2 is falling, okay, it's exerting a torque with a force equal to m2g times the radius of the wheel. But for the massive rope, because the rope is massive, this chunk of rope has a mass m2, but then there's some more rope over here, right? So as this wheel starts to unroll, the mass, the torque being exerted on the second figure, on pulley 2, the torque is increasing, right? So the torque on pulley 2 is increasing as the hanging rope, or I should put the hanging piece of rope or hanging section of rope is getting larger or longer. It is getting longer and increasing in mass. And increasing in mass, which means it increases in weight, right? So this pulley 2 is going to get pulled harder than pulley 1 at some later time delta t, and holding everything else equal, that'd mean that the angular speed is greater for pulley 2 after some time delta t, and that's the reasoning behind it. And then here we have this equation, and we need to derive an equation for the angular acceleration of the pulley as a function of time and express your answer. All right, so for this one, we just have to take the derivative, right? So we're going to take the derivative of this function here. And again, let's remember our power rule in order to deal with the exponential. So I know that alpha is equal to d omega over dt. And let's just write it out. So d over dt of m2 over 2 lambda r times c, okay? And then I'm going to take the derivative of these. So I have CE to the t. So CE to the t. And then here I have, CE to the CT. So I have CE to the C times t minus negative C times E to negative C times t. Okay, so I have minus negative C. Whoops. I wrote this here. All right, so I already started taking the derivative at this point. So I take the derivative of the function, and the only thing that really changes are the exponentials, right? Because there's only ones that have time in them. But I'm kind of working this out. So what I can do here is I can factor out a c. Okay, so I have c squared. So I have m2 over 2 lambda r times c squared times e to the ct plus e to the negative ct. All right, so don't forget to distribute that minus sign. So we got to distribute that minus sign, and then we end up with this expression. And this is my angular acceleration. And use the expression for c to write alpha 2 in terms of this. Oh, wait, no, that's for the second part. Express your answer in terms of c, m1, m2. Oh, yeah. So first part, we just take the derivative. All right. Now what we have to do is figure out what c has to be. So to figure out what c has to be, what we need to do is, so this is our expression for the angular acceleration, and we have to relate it with the expression for the torque on the wheel. So I know that torque is equal to I times alpha. I have here this expression for alpha. And basically what I'm going to do is I'm going to set this equal to the force acting on the wheel, right, which is just m2 times g times r. Whoops, I skipped something. So m2 times g times r. So the force acting on the wheel times r. So I have m2g times r, right? And the moment of inertia of the wheel is m1r, 1/2 m1r squared, because it's a solid disk. Okay, so this is equal to 1/2 m1r squared times alpha. And we need to come up with an expression for C. Let's see here. To write alpha 2 of t. All right. So here, let me resolve this. So here I have alpha is equal to, so one of the r's are going to cancel out. So let me just do that. So one of the r's cancels out from this expression. And then I have alpha is equal to 2m2 times g over m1. All right. So that's my expression for alpha. And what I can do in this case is, so let's think about how to solve for C. So I know that at t equals 0, okay, that these exponential terms, so this is the initial angular acceleration. And I guess the idea with this is that the angular acceleration of pulley 2 is going to increase. So this function here, e to the ct plus e to the negative ct, okay, you may wonder what this function looks like. So you can always just graph a function to get a feel for it, right? So if I graph e to the x, obviously it's going to be blowing up. And if I graph e to the negative x, it's a decaying exponential, right? So what happens when I combine both? Well, it's actually pretty interesting. It approximates a line for the first part, and then the exponential term just kind of blows up. And the reason for that is if you think about what e to the negative x, what happens to e to the negative x, right? So it starts off very large, okay? But basically what happens is it approaches 0, right, as x approaches infinity, but then e to the x kind of blows up, right? It's, e to the x, e to the, some value is going to exponentially increase, quite literally. So this is what the function is going to end up looking like. So then here, in order to solve for C, what I'm going to do is I'm going to set t equal to 0. So I'm looking at the initial angular acceleration, and that's going to allow me to solve for C, right? So I have here 2m2g. Wait, hold on a second. I messed up one of my r's. So I have m2g times r. I got rid of one of the r's. Yeah, I forgot an r term here. That's my bad. So here I have alpha is equal to 2m2 times g over m1 times r. And then I'm going to set that equal to the expression for alpha. So that's equal to m2 over 2 pi, not pi, what am I saying? 2 lambda r times c squared times, so at t equals 0, right? So we're going to look at the initial angular acceleration. So at t equals 0, I have e to the 0, which is 1, plus e to the negative 0, which is also 1. So there's just 1 plus 1, which is 2. And that 2 cancels out with this 2 over here. Okay, so I'm going to write this as m2 over lambda r c squared, which is equal to 2m2g over m1. Right, so 2m2g over m1 times r. And then one of the m2's, so I'm going to start canceling some terms out here. So one of the m2's cancels out. One of the r's cancels out. The r cancels out over here. And then I get c squared is equal to 2 lambda g. So c squared is equal to 2 lambda g over m1, right? Let me double check that. See, I get 2g lambda over m1. Yeah, 2 lambda g over m1. Perfect. All right, so then that means c is equal to the square root of 2 lambda g over m1. Then we get to put it all back into the original expression, which we'll do here, okay? So we have the expression I wrote up here for alpha, so the m2. Let me just kind of write it out over here. So as expression of t, All right, so I'm going to write these expressions so we don't lose track of them. So I have m2 over 2 lambda r times c squared times e to the ct plus e to the negative ct. All right, that was my for part 1 of part B. And then for part 2 of part B, I now figured out what c is. So now if I put that c squared term back into the original expression, I'm only going to look at this first part here, right? So let me put this in like a different color to emphasize it. So I'm going to look at what happens when I take m2 over 2 lambda r times c squared, where c squared is 2 lambda g over m1. So let me do that real quick. So I have m2 times, divided by 2 lambda r times c squared, which is 2 lambda g over m1. Well, the lambdas cancel out. The 2's cancel out. Yeah, just the 2 lambdas. So I get m2g over m1r, right? Yeah. Yes. Okay. So I have m2g over, so let's see here. So I have m2g over m1r. And then I'm going to write that out here, right? So let's see here. So now alpha is equal to m2g over m1r. Okay, that's now this coefficient times the c squared, where we figured out what c squared has to be. All right, this now times the exponential terms. So now I have e raised to the square root, yeah, there's not much space here, 2 lambda g over m1 times t plus e to the negative square root of 2 lambda g over m1 times t. All right, there we go. That's our expression. And now a third pulley has a mass 2m1 and a radius r as pulley 2, at the same radius r as pulley 2, and the rope of the same linear density lambda is wrapped around pulley 3 with a rope section of mass 2m2 initially hanging from the pulley. Pulley 2 is returned to the same configuration at time t equals 0. Pulley 2 and 3 are released simultaneously after a long time after being released, but before the ropes are completely unwrapped from the pulley, indicate whether the angular acceleration is greater for pulley 2 or greater for pulley 3. So this goes back to what I was talking about with the graph. So we know, basically, here's the reasoning for it. So pulley 3 is twice as massive as pulley 2. And the rope section for pulley 3 is also twice as massive. So a knee-jerk reaction may be that they're going to be the same. But we have to look at the function. All right, so we have to look at the function. Let's replace the terms. All right, so let's look at it for both pulleys. For pulley 2, right, so for pulley 2, it's going to be, well, the expression that we have, m2g over m1r, blah, 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 right? Now, for pulley 3, right, so let's write it for pulley 3. Let me use a different color for pulley 3. So for pulley 3, instead of m2, I have 2m2, right? And instead of m1, I have 2m1. So for pulley 3, the angular acceleration, maybe green is not the best color. Can I have like a dark green? I'm not going to play around with this too much. All right, I'm just going to keep it. I want to make sure we're almost done. Okay, so for pulley 3, let's write the expression. So now I have alpha is equal to 2m2g over 2m1r. All right, so we see that this coefficient, right, the 2's are just going to cancel out, so they don't really matter. But the exponential terms don't cancel out. They are going to be different. So this has to do with the rate of change of the angular acceleration. And now I have square root. So the lambda stays the same linear density, same gravity, but now it's not divided by m1, it's divided by 2m1, okay, times t. And this is going to be the term that dominates as t grows, right? So as t grows, this positive exponential term is going to dominate, and it's going to grow at a different rate for pulley 3 than for pulley 2. For pulley 3, it's going to grow at a slower rate because the exponential is smaller, all right? And then the decaying exponential, I'm just going to write minus ct. This one's not going to matter because as t approaches infinity, this term is going to approach 0, right? So e to negative infinity is 0, whereas e to the infinity is not 0. It's infinity. So that's the reasoning. So in terms of justification for the answer, you would say that the coefficient is the same, right? The m2g over m1r, that's the same. But for pulley 2, what I have is the term that dominates is e raised to the square root of 2 lambda g over m1 times t. But for pulley 3, it's a smaller term because it's only 2 lambda g. Actually, I'm just going to cancel out the 2's, right? Because it's 2 lambda g over 2m1, right? So basically, it's just the square root of 2 lambda g over m1, right? So the difference in the rate of growth of both of these functions for pulley 2 and pulley 3, basically the angular acceleration of pulley 2 is going to grow at a rate, right, at an exponential rate of square root of 2 faster than pulley 3. And if you think about it, so, I mean, there isn't really any intuitive reasoning I can give for it other than the fact that this is a solution of a differential equation, and if you look at the rate, you get these exponential terms, okay, of how the angular acceleration increases. And honestly, this is part of the reason why math is so important in physics, because a lot of time there isn't a super clear-cut, clean intuition behind some of the problems, and you just have to look at the solutions of the equations to see the rate of change of the angular acceleration. I guess one thing that can be kind of thought about is, like, let's imagine that the pulley was really, really, really small, or it had a very, very, very low mass. Then the angular acceleration would increase tremendously. But basically, the answer is that it's not a linear relationship. That's just how it is. So if you had a linear relationship, right, I could double the mass of the pulley, double the mass of the weight, and I'll get the same proportion, the same ratio, because that's what linear is. With these functions, the more complicated mathematical relationships, you're not going to have these kind of one-to-one comparisons, right? You have to look at the function and you have to understand how the function behaves across the domain. And it just so happens, because of the exponential term, this first exponential term is what dominates. For pulley 2, the angular acceleration is going to grow at a faster rate than for pulley 3 because of this exponential term. So yeah, that's pretty much it. This one was a bit of a doozy. I feel that conceptually it was not terribly difficult. It was more difficult in terms, I would say it's more annoying than it was difficult, right? Just because there's a lot of math you have to do, right? You have to take in the derivatives, and you have this, big function, and it looks intimidating. But just take it slow, pace yourself, double check your work, and try not to make any mistakes. Conceptually, these problems were not terribly difficult. The lab question was a little tricky. But I know this video went a little bit longer than I anticipated, but it's important that we understand the problems. And what I'm probably going to do on Friday is look for another good practice FRQ that we can work on together, and look at the scoring guidelines and self-score and make sure we really know how to do this. But yeah, I mean, that's pretty much it. If you have any questions, just let me know. There's plenty of time to review. You have the weekend. I mean, I'll be after school tomorrow and Friday. So I can also help out during that time. And our test is actually first thing Tuesday, I believe. So there's also Monday if you need some help. But yeah, that's pretty much it.